Okay, so today we are going to do a little bit on visualization, and we do have a guest speaker, Alberto, who is in the class as well. He's a grad student. Yay! He doesn't work with me, he works with Jason, who is the visualization expert, so that makes him a visualization expert. Relative to me, and to most of you. But before I get to him, I do want to sort of quickly motivate why I wanted to actually get him to talk about this topic, and why I thought this topic would be interesting. Okay, hang on. It was basically this. I was looking at, a couple of weeks ago we were talking about LSTMs, long short-term memory units, so the deep learning stuff. And I was looking at there's like 2 Google papers on their neural machine translation system. And just a quick thing, this is the architecture diagram of their system. They have these LSTM systems, LSTM units that are hooked up each of these rectangles is an LSTM unit, and they have it hooked up in actually the first layer where the inputs are your x3, x2. Those are your words, your actual words in your speech or in your sentence, right? And that goes this way. So they have a unit here going this direction, and there's another layer going the other direction. Okay, so that's actually quite interesting. So they actually have two sets of LSTM, one for going forward, one for going backwards, right? And the intuition for that is that the dependencies of words, right, oftentimes is not just a sequential dependency on what goes before. It can also be what's coming after, right? So the meaning of words, often it's the context for it is not one direction. It's actually both direction. So that's why they had actually these multiple direction units, right? Then they have multiple layers stacked on top of it, and with these what's called residual units, which you saw last week from Jonah's lecture as well. And so this go up into something fairly deep, and they're using GPUs for each layer here, as you could see, 8 layers, and then it goes into this is their internal representation, and that goes into some kind of attention unit. The attention unit tells, basically encodes which part of the sentence to focus on. That's why it's attention. Like I'm focusing my attention on the first 3 words, focusing my attention on the next 3 words, and so on. Right? So this attentional units tells it where to focus on, and then it goes into a decoding unit. This is where it then, so this is one language. This is the source language. This is the target language. They sort of do the same thing to sort of encode up into this level, into this deep internal representation, and this attention thing sort of creates the connection between them. So in a sense, it's like I have got these semantic representation of the sentences in some high dimensional space. Okay, which are really these are the things. These are the outputs here actually. All right. So the translation is actually going then from here to this side, which then goes back here into the translated sentence. Okay. But just to keep things short, residual connections. These are sort of the jump aheads. This actually helps with back propagation of the signals in training, so that's why they're doing that. The bidirection I mentioned before is to capture left and right contextual dependencies. Okay, very cool stuff. But then they did something pretty cool, I thought, was that they took the internal representation of the sentences, right, which are in high dimensional space, because those are like vectors of like, at least 1,000 dimensions kind of thing, right? And they use this system called TSNE, TSNE, and they map those sentences down to a two-dimensional space for visualization. And interesting stuff was that they found that the sentences for the same topics, right, and for the same then for the same topics, and even in multiple languages, the same topics, they tend to cluster together. Okay, so this was sort of their cool representation that sort of showed that. So if they zoom in on this, you have this, and if they break it down, this cluster of each point is a sentence, or is a deep representation of the semantics of the sentence, of the meaning of the sentence, right? So each point is a sentence, and if they then color the points based on the languages, right? So you have Japanese, Korean, and English, and these sentences cluster together, and these sentences happens to be the ones that are translations of each other. So this was sort of pretty cool. So in a sense, the visualization of high dimensions becomes actually useful in like in this case to sort of use this as a sanity check, a sanity check of what's happening. And by the way, this is probably the thing that also created, if you remember, like beginning of this year, there was a news that Google Translate has their AI has created this language agnostic representation of human language, pretty much. What was it? I think it's Yahoo. I think it's Google. Yeah, Google Translate. So I think this is what gave rise to that, right? So this is basically saying, oh, they have these internal representations that represents the meaning.
They were really happy about that because the people that study languages, they don't think there is a relationship between all the semantics.
Yeah.
So they were saying that there is actually some connection at a lower level of all the semantics of all the languages.
Yeah, which I thought was really cool. Anyway, so this is my segue into Alberto, who is going to talk more about this stuff. All right, so I'm going to let him take over. Let me just put him present.
Thanks.
Oh yeah, just take
a little bit maybe, no? Yeah. Okay. So hi.
Yeah, you can stand. You have to
yeah. Try to do this the best I can. I had to prepare this really fast. I actually prepared this in like 1 day and a half or something like that. I didn't know exactly what to talk about. So first I was thinking of making like a general thing about visualization, but that was mostly talking about like things about the brain and how we process information and stuff like that. It was a bit weird. So eventually I tried to focus on this specifically. The class is about data mining. We have like a lot of data with a lot of different attributes. And what's the challenging of visualizing like data like that? So I'm focusing a little bit on what's called visual analytics. So this is not like exactly a new term, but it's like getting really hyped right now. So the idea is that when you're doing what we do in this class, when you're analyzing data, most of the researchers tend to do things numerical. So you're working on Python or whatever, and you're looking on your data, then you look at a few numbers, you compare the values, and then you continue doing your process and your modeling. And what visual analytics is trying to tell you is that you should be visualizing each time that you try to change your data or you're modeling your data, so that you can see your changes and then go back to the numbers, visualize again, and change them. So it's basically kind of like this process. So you are visualizing information, then you interact over that information, you do some data analysis, you visualize again, and that's kind of the process that you should be working with. So the definition is visual analytics is the science of analytical reasoning facilitated by visual interactive interfaces. And why it's important to do visualization and not only just numbers and analytics. So I got these two quotes here. So this guy, Jan Piagnet, was a researcher that basically focused on teaching kids learning methods. And he kind of discovered that human beings are really good at remembering stuff when we see it. So that's what he called object permanence. And then also he says that humans create mental models of the things that you have already seen. So usually when you see something and then you see something new, you kind of construct the new things that you're seeing based on your models of your past models. And it's been proven that your models are much better, or you get better insights when you're visualizing them than when you're looking them only on numbers. And this guy, Richard Hamming, basically said this, that the purpose of computing is insight and not doing numbers. So it's kind of what we're advocating, visualization. No? So why visualization again? So it's visual information is our primary sense. So human beings basically get all the information from their eyes. What I'm visualizing here basically is what's called the conscious bandwidth and the subconscious bandwidth. So this has all the senses. So this is sight, kinesthetic of touch, sound, smell, and flavor. Basically, as you can see here, most of the bandwidth is used by the vision, and then by the hearing, and a little bit of touch. That's the conscious. When we're looking at the subconscious bandwidth, that's mostly of what we think about. Basically, all of it is visual. And what do I mean by conscious and unconscious? So this is what I mean by conscious and unconscious. No? When human beings are really good at detecting patterns. So when you see a tiger, you run away. When you see something like that, those two numbers, you have to stop for a second, make the calculation, no? And then you say, oh, fuck, my factory is going to blow up, so I better run. So that's why this visualization usually is much better and faster. Another thing that we talked in class, and somebody mentioned the other day, is about like how you get the information from the images and things like that. So the first thing for visualizing things that are not numerical is doing some kind of transformation. So usually when you have things that are time series or signal processing sounds or things like that, what you try to do is look for patterns. I mean, we talked about all of this in class, but it's just looking for patterns, then you find a pattern and you try to transform that pattern into numerical value. So that could be a vector, you could do a histogram of that, and then you try to visualize those vectors using all the parameters. Other options for images, usually what they tend to do is they look at the individual pixels, they look at the luminance values, black and white, or they look at the luminance values on the red, green, and blue. In text, usually what you do is you get the text, no? Then you get your different attributes based on the terms that you have, so the words, and then different documents. So here you can see why multidimensional data is important, because all of these data sets, basically, they are multidimensional. We're talking about vectors, we're creating pixels here, and we're getting words here. So that's like, usually when you're visualizing, for example, text, you're gonna have thousands of words there. So you're gonna have thousands of dimensions. So why doing this is difficult? It's difficult because basically when you're visualizing something, you're projecting all of those data points into a lower dimensional space. When we do this for all dimensions, usually what happens is that things that are close to each other as we sit in class may be very far apart from each other in reality. The problem is that humans lack the capacity to see this in more than 3D dimensions. So we either get like little kids and teach them to see like in hyper dimensions, or we create like different techniques for visualization to try to fix this. And from now, the basic term or the only way of trying to cope with this is adding interactions to the visualization. So the idea is you have to select different projections, and then you're going to interact over them, see how the data points are moving, and that's going to give you an idea of what's happening, even though that you're not seeing all the dimensions at the same time. So I mean, we've seen this. This is like the simple stuff that you have. You have scatterplots. You have different attributes in different axes. Usually there are two. You have also sometimes three if they are three-dimensional. Again, the problem here is that it might be like points that are very close to each other here in the multidimensional space might be very far apart from each other. So when you're looking at this, you might think that all of these points are really similar, when in reality they are not. They are just similar related with those dimensions. What people do when they have this problem and you have scatter plots is this one. You use what's called the small multiples. They don't use this only with scatter plots. They do this with any kind of graph, so you can see this with line charts or bar charts or histograms. They try to create kind of a matrix display and then put all the attributes in the different spaces. So what you have here is, if you look vertically, all of this is horsepower. All of this in this direction is weight. So this would be horsepower against weight. This one would be horsepower against acceleration. So what you're getting here is that you see a lot of attributes simultaneously. You can get a lot of different comparisons and get correlations. I don't know, you can see like, for example, lower horsepower corresponds with lower weight, higher horsepower, higher weight, and things like that. The problem here becomes when you, instead of having 4 or 5, you have 100. Because then you have like a picture like this one with all of the scatter plots painted there and you don't see anything. So that's the main problem. Usually what researchers do here is they try to select the most important dimensions, and then use them to plot them pairwise. This is probably the most used technique, I'm guessing. So most of the times they use scatterplots, and this is the most simple thing to do. So what's projection pursuit? So the problem about that is that you have a lot of different projections. So, and it would be wonderful to know which projections are better than others. Some of them are not telling anything. If I go back, some of them are repeated here. I know you have horsepower, weight. So you're repeating a lot of graphs. And then some of the information here, like this one here, I'm not telling you anything. So these guys, Friedman and Tukey, in 1974, they came up with the idea, and they said, oh, maybe we can get a computer to help doing this. No? So maybe we can use some algorithms, right, on the scatter plots, make some calculations, and then decide which scatter plots are better and worst. So that's what they call down here scagnostics. This is kind of a statistical term, but now in visualization it's pretty fancy too. Basically what you do is you got all your hundreds of scatter plots, then this thing, scagnostics, is just basically like 10 types of numbers. You run your numbers on those scatter plots, and then you say, okay, these are my 10 most important scatter plots, and then you draw those ones. The idea is that they got like different parameters, like the spreadness of the data, the clustering of the data, and things like that, so it gives you like different graphs with different properties that are interesting. Distance consistency would be like a simpler way of doing it. It just would be like one thing, and you're just trying to keep the same distances with all the data points. We've seen this in some of the techniques. So now I'm going to talk a little bit about all of these projections. So the simplest, or the initial one, were these guys that basically thought about, instead of showing the projections all at the same time, they said, okay, we're going to try to create a story with the projections. We're going to select good projections, and then we're going to show the projections to the user in certain order. With that, what happens, and you're going to see it in the video, is that the data points move around. And then you get that interactivity that allows you to see, when you're moving the dimensions around, how they are affecting one to the other. So this is done in 1985, so it is pretty old. I'm not going to do it with sound. I'm going to go over it, just playing a little bit of what's happening. I'm going to get up. Okay, so basically I'm going to put this big. They are selecting different attributes there on the... Okay, so they're selecting different attributes. You have all your database there with all the information. The top 3, they are just categories. They are selecting the different categories. They have different colors. That's what they're telling you there. And then you have all of these ones that are the numerical values. And what he's trying to do is trying to visualize all of those attributes together. So now he's going to select them. Going to go a little bit faster. He's going to select them there. And then as you see there, he's selecting all the attributes. You see in the bottom how the visualization is changing. I'm going to stop for a second. You see here on the bottom, here, these are the axes. So while he's selecting the stuff, you'll see that this begins to grow and appear more of them. So you have 1, 2, 3, 4 here. And once, you don't see it pretty clearly, again, this is pretty old, but it's rotating and it's doing like a 3D rotation, even though you see it in 2D. So if you see them there moving around, you see the 3D there, how they are like kind of rotating there. All the axes together, and by doing that, basically all the data points are moving around. This is not optimized with any projection, it's just using the basic axis, so that's why all the points are kind of clustered together. These guys also added a new functionality here that they saw at the end, that they do the same thing, but they project in PCA. And once they do the projection in PCA, you can see them here. The clusters begin to separate a little bit better. But this is something that I wanted to mention. So you saw that the axes were there before because they were using the normal axis with the normal dimensions. Once you do something like PCA or some transformation like that one, you lose that. So there is no more axis here. So it's good because you can see that the points that are close together, they are similar. The problem now is that you don't get like a sense of what's happening around it. When you're looking at a graph, at a scatter plot before, and you had your axis, you know the things that are in the top left are going to have high value there. But you lose that here. You don't know if these points here have a high value of something. You just know that these 2 points here are similar. So this is the problem when you're doing these types of projections, and this is mainly the big problem with all the multidimensional projections, because the ones that are actually creating good clusters lose the information of the attributes. So a little bit more optimized, you see there, basically you see there how they separate the whole clusters eventually at the end. No? So this would be one of the options. No, you have like different projections, and then, and then basically you loop over them. What? So now I'm going to talk a little bit about the projections. I'm going to go fast here because we talked about this in class. No? But the idea is that you have different, instead of projecting on the axis, you can project on different abstract axes that are going to give you something better when you're looking at the point. So for example, PCA, basically what it's trying to do is enhance the variance of the data. So you're trying to spread all the data points as maximum as you can, so that you can see how spread they are. The idea is that you're making a transformation, so you're getting the new set to be transformed into these principal components. They say that they are uncorrelated with each other because PCAs are orthogonal. So that means that they try to project them into axes that they don't have non-correlation between each other. So this would be an option. You could use this as you saw before with grantors, for example. No? You're just looping through different types of projections. In this case, you would calculate like maybe 5 PCAs, and then you would loop over those 5 PCAs so into the user. LDA is similar, but it's for classified data. It's the same thing. You reduce the dimensionality to k dimensions. Here you minimize the variance between the clusters and maximize the distances between them. So usually tends to produce more compact clusters than PCA. So I mean, if you know your data and you have already classified your data, this is probably better. If not, use PCA. The third option, I think we didn't talk about this one in class unless it was here. But this was kind of an old approach. They were using neural networks here. What they do is the same thing. They use neural networks to reduce the dimensionality of the data set. What you see on the right is a visualization of different people. I think it's in the Senate. So the first one here, the first visualization, showing you the cluster that the computer made. So the SOM automatically. So what you see is the elements that are here in the left are very similar to each other, they're in the right similar to each other, and in the middle there has to be a difference. So that's what the second one is showing you. Second one is showing you the difference between the clusters. So as you can see, the things that are in the left are pretty bright, and the things that are a little bit here in the right, they are also bright. And here in the middle, they are a little bit darker. That's because that's the difference between the two clusters. So the elements that are here together with each other are basically much more different than these two elements that are here with each other. Then they did a classification, looking at the party. So they tried to predict by this clustering which party they were in. And again, they did a very good prediction on this part here, good prediction on this part here. In the middle, they have more problems to predict which party you are in. And from there on, all the rest of the graphs, basically they are just voting graphs. So they are like visualizing what do they expect from the people to vote. So for example, I don't know, this one here, that's border protection. So you can see that the Republicans mostly are going to vote yes for border protection. Most of the Democrats are going to vote no for border protection, and then in the middle you're going to have indecisive people. So basically what self-organizing maps is doing is moving all the data points around and then putting all the things that are similar together. But you're losing the information about different clusters or how they are arranged in the space. You don't get that information here. You just know that the points here seem to be very similar and the points here seem to be similar to each other. From here, the researchers begin working on what's called manifold learning. So an example of this is TSNE that I'm going to talk in a sec. The idea is that most of the data sets we're talking about, they have a lot of dimensions and they are multidimensional. But looking at the maths and looking at those dimensions, actually that's not real. That's what manifold learning is saying. Most of those dimensions are actually related with each other. So once you know that two dimensions are related with each other, so if you know that something it's positive correlated, so I don't know, like weight and acceleration that I was talking before, no? So weight and horsepower, I think it is. So cars with higher weights usually have higher horsepowers, no? So knowing the weight, you know the horsepower. You know that if you have a higher weight, you have a higher horsepower, so you don't need both of them. So that's what this is doing. It's trying to look at all the attributes and saying, okay, I can get rid of all of these attributes because basically they are not giving me anything. And the good thing here is that they are very good at detecting nonlinear structures that the other algorithms that I mentioned before are not so good at detecting. And also they can classify elements in different clusters. So multidimensional scaling was pretty famous too. It's pretty well used. Now most of the people are using TSNE, but this was kind of the standard. The idea is the same thing as before. You're trying to reduce dimensionality to 2 or 3 dimensions so that you can visualize them. You do this by visualizing the similarity of the elements in the database. So again, you lose the context of the information. You don't know if the points have higher values or lower values for some attributes. You just know that the elements are similar to each other. The next option is to distribute the stochastic neighbor embedding, so TSNE. And I mean, you see there is 2008, the algorithm, but now in the last probably 2 years has become like really, really famous. That's because a lot of deep learning algorithms have a lot of dimensions, and this thing performs really good at doing that. So again, it gets like a lot of dimensions, try to simplify all of those dimensions into a 2D plane. The way that it does that is it converts all the data points or the affinities between those data points into probabilities. Those probabilities, they represent them as Gaussians, and then the affinities are represented as T distributions. And the joint thing between those two gives a very good local structure detection, and also reveals patterns and elements that are in multiple clusters. And something that's really important, it reveals multiple scales in a single map. So when you have like very small clusters compared with very big clusters, it's actually able to detect both clusters, even though the spreadness of the clusters is very different. So the most important parameter of this thing, I don't know if you talked about this in class, but the thing that they mention all the time is this parameter called perplexity. So it has 3 or 4 more parameters, but this thing basically what it's telling the algorithm is how to detect the clusters. So perplexity tells it like how clustered the elements are. And playing with that value, you basically enhance the local structure or the global structure, depending on what you need. The problem of the algorithm is that it's not the same output for each run. So depending on when you run it, you're going to obtain different results, similar but different. And also this perplexity parameter, as you see here, changes a lot the result. So usually they tell you to plot it or visualize this with different perplexities and then work on it and then decide which one seems to be more formal. So these guys, I found this yesterday, it was pretty interesting. They made like kind of a study, so they begin with, this is what I begin with, no? I know that the 2 clusters are here, I mean, this is not what you do, no? But this is to show you what TSNE is kind of doing. So if you have like a very low perplexity, all of them are 5,000 steps, but then the perplexity is kind of growing. So when you have a very low perplexity, the system doesn't detect anything, it's not able to detect any of the clusters. As you keep rising a little bit the perplexity, suddenly here you see that the system is able to detect the clusters, but the form of the cluster is a bit weird. Getting up, you continue to detect the clusters, but you lose a little bit of that form too, so the clusters are much more clustered there. And this one here with a 50 kind of seems like more accurate compared with that one there, but it's difficult to choose, you know, it's difficult to say which one is the good clustering method, no? I mean, this one's, you have to think that this and this is kind of working, because what you want to do is separate those points, but you would also like to know how different they are, no? So if maybe you're seeing this here and you think that they are more different than this one here because they're a bit closer, I don't know. So that might be a bit problematic. Another problem with the algorithm is that what happens when they have different cluster sizes, no? So as I was saying before, it's able to detect both cluster sizes, but you lose that reference at the end. So when you're visualizing the end, it might happen that they look like that in TSNE if you find a good perplexity argument, but if your perplexity value is different, you know, and they put 100 there, but they don't tell you that it has to be 100, you have to play with that. It might be a different form, so you might lose that information too. Again, the distances between the clusters might not mean anything, and that's a problem because that's kind of what you want. You want to detect the difference between those clusters. So as you can see here, no, blue and yellow are very close together and the green are separated. Lower perplexity, no clusters. A little bit higher, we see that the clusters are being detected, all of them equidistant, so the distance is lost. The clusters appear more compact here, but not equidistant, the same thing, so you still have the same problem. And suddenly here with 50, you see that that one behaves much better like the original. So you have the blue and yellow very close to each other and separated from the green. So that's what you would like kind of here. And then also the shapes. So when you want to detect the cluster, usually you want to keep shapes, no? As you can see here, it's kind of complicated because in the perplexity 30, they seem that they are kind of good, but then you go to perplexity 50 and they're wrong, and then you go to 100 and it seems like it's behaving like perfect, like the first one. So those numbers, they are changing. So sometimes here is the 30, sometimes here is the 100, so that's the problem. Again, you cannot have everything together, so this is very nice because you're getting a lot of dimensions and kind of separating all the data points, but it's difficult to interpret what you're looking at. So I got this video from Google. I thought this was the one that you mentioned the other day. I saw this at the beginning of the year, yeah. It's kind of cool. So they did they visualized the information in 3D using TSNE. I'm gonna leave the audio feed. don't know if it's going to be loud enough.
Machine learning is pretty
No,
complex.
it's not. No.
So we've been experimenting with ways to visualize what's happening. There's a core concept in machine learning called high dimensional space. Here's one way to wrap your head around this concept. You can think about people as being high dimensional. For example, take famous scientists. You can think about when they were born, where they were born, their fields of study. Each of these is like a dimension of that person. These dimensions become difficult to untangle when you think about different people, because someone might be similar in some ways, but very different in others.
But this is the kind of thing you can use machine learning for. With machine learning, the computer isn't told the meaning of these dimensions, it just sees them as numbers. And it sees each set of numbers as a data point. But by looking across all of these dimensions at once, it's able to place related points closer together in high-dimensional space.
Here's a concrete example where words are treated as high-dimensional data points. The important thing to remember is that we haven't told the computer the meaning of words. Instead, we've shown it millions of sentences as examples of how words get used. Here's a visualization of the results. We're looking at a subset of words that the computer has learned about. Each dot represents one word. Each word is a data point with 200 dimensions. Using a technique called t-SNE, the computer clusters words together that it considers related, and clusters form based on meaning, even though we've never taught it the meaning of words. Here is a cluster of numbers, months of the year, words related to space, people's names.
As you can see, I mean, all the things are together, but there are no axes here. So again, you're losing all of that information. No? You get like all the
cities,
things together, but
and so on.
We can also look closely at smaller sets of words. If we search piano, we can run t-SNE only on words related to piano. We get clusters of composers, genres, musical instruments, and more.
And this approach doesn't just work for words. For example, you can also treat an image as a high-dimensional data point. Here's a data set where lots of people wrote digits between 0 and 9. People write in all kinds of ways, so the question is, instead of us needing to manually code rules for all the ways people write, could a machine figure it out itself using machine learning? Each image is 784 pixels. The computer treats each pixel as a dimension. Again, using t-SNE, it clusters these images in a high-dimensional space. We've color-coded them so that it's easier for us to see what's going on. And you can see groups of digits clustering together. It's learned something about the meaning of these digits.
These visualization techniques we've been exploring can be useful for all kinds of things. That's why we're working on open sourcing all of this as part of TensorFlow, so that anyone can use these tools to explore their data.
Okay, so well, you see it there. I mean, that's kind of this became like a really hit video at the beginning of the year from the Google guys. If you want, I'm probably gonna share this thing too. So I'm not gonna play this one because this is an hour video, but they make like a good explanation of all the stuff that they are doing there. So again, it's really popular because it's really powerful. And you can really use it for a lot of stuff, and it's just running an algorithm that basically tells you all the points in lower dimensions. So once you have it, it's just plotting those points with the coordinates values that it gives you. Okay. Yeah, it is. It's awesome.
I don't believe you.
So yeah, I mean, again, those things are very good for seeing these things. For machine learning is very interesting because you're seeing things that are clustered together, and most of the times you want to detect clusters. So that's kind of the important thing. If you're trying to understand behavior, it's complicated because you understand that those points are similar, but you might have a cluster just by the side of that, and then you don't know what's the difference between those two clusters. Okay. So this is something different. They're forgetting projections, and now we're going to back like classical stuff of visualization maybe. So this is another option. I don't know if you guys seen this before. It's called parallel coordinates. What you do here basically is you get all of the dimensions and you paint a vertical line for each of the dimensions. No? So you have mile per gallon, cylinder, horsepower, weight, year, vertical line, maximum value, minimum value, and you have that in all of them. What you do then is each of these lines is a data point. You say, okay, this car here has 9 miles per gallon, and then it has 8 cylinders, and then from 8 cylinders it has 450 horsepower, and so forth. This is pretty useful when you have a lot of data points and a lot of dimensions too. The big problem that you have with this thing is that you have to really think about the order of the attributes that you're putting there. Because if we begin shifting these columns around, the graph totally changes, and then you're gonna get a lot of crossings. For example, here the video right, so you have like crossings up and down, and you kind of get an idea that cars with high mile per gallon usually have higher cylinders. Lower mile per gallon has higher cylinders, and the other way around here. But if you choose different order of the axis, you might lose totally that. And then you have a lot of crossings, and you have something like this here, and then you don't see anything. What people do here is they try to maybe plot or diffuse like the amount of lines. So instead of putting all the lines, you would see like a darker blob here going up, so you can like get trends of the visualization. This is kind of classic. So you see that in 1990 is really well used too. You see this all the time. Probably with the scatter plots, this one is the other one that people choose more. So and when you're visualizing things, if you don't want to visualize a lot of stuff together, usually don't do so much. So you visualize like 4 or 5 things, and this is pretty good for doing that. Okay. Again, if you have any questions or whatever, just let me know. Star coordinates. So this is another option for plotting stuff all together in 2 dimensions. This is a little bit different from the other graphs. Here, what they do is basically they put all the axes in the graphs, but the axes don't have to be orthogonal to each other. So you can see here, this is mile per gallon, this is price, horsepower, fuel tank capacity, and turn cycle. And then when you finish looking at the visualization, you have like elements that are very similar to each other get together. So all of these points here of these cars are similar, all of these cars are similar. But you lose one concept here again, is that you don't know if this car here, what's its exact value of price, of horsepower, of fuel tank capacity, right? You don't know its exact value for any value. The way that this works, I'm gonna show it in a second, because probably I was gonna explain it on high, but I found this video, it's probably gonna be easier. So it's called vector summation, the way that they do this. Oh, sorry. You have to imagine that what they are doing is just getting each of the values for each of the axes, and then they are putting a vector on that axis, and then they make like a summatory of vectors. And that's what the point ends up being. It's gonna make a sense in a second because they drew it here. Come on.
Star coordinate.
Yeah, so you see there what it's doing. That's what I mean by summatory of forces. So if you see there, you have all the dimensions here plotted. So this is 1, the 2, the 3, and so forth. So what it does is says, okay, this is my value for the 1. Then it projects on this dimension here and says, this is my value for the 2. So imagine this is 0, this is 1. And you say, okay, for the 1 I have 0.2. For the 2 I have 0.4. For the 3 I have 0.5. And you go like that. So that summatory of points eventually puts this point in a position. That position is giving you the information related with all of the attributes. So if you have like this element here, probably it's going to have a D4 stronger than a D8. And these values here are going to be stronger than these values here, because it wouldn't end up here. So you know that if you have a lot of points here or other points here are going to be similar to this P. But you don't know exactly what the values of those points are. So they might have totally different values, but in average, all of the different dimensions sum up to be something very similar. So this is very good again to detect like points that are similar to each other. So again, if you go here, you see all of these points here are very similar to each other, but you don't have an idea. Here they do the same thing with a lot of more dimensions. It's very difficult to interpret like why these points are similar to each other. So the way that they solve that is with some interaction that you're going to be seeing in a second. Is that clear, like how they put the points? So it continues doing like that, and you see that how it gets moved and positioned. No? So you can stop. Okay, so they say, yeah, we can do this with a lot of dimensions. That's the good thing. No, we can put 10, we can put 100, we can put 200 or 10,000. Yeah.
Really?
Yeah, I don't understand this part, no, because it's really, again, so yeah, you can do this. And okay, the more that you put, you see that all the points tend to go up to the same place, because it's happening the same thing that with multidimensional space. Then when you have too many of them, it's too many. So all the points tend to go to the same directions, because they are going to have like some attributes that are higher than the rest or stuff like that. So I wasn't really clear when they were doing this. I guess they were just bragging a little bit. But I mean, you can say that these 2 points here are similar. But again, you have so many dimensions that it might be that they are not. They just have two dimensions close to each other, and those two dimensions have similar values, but they are not the same dimension.
So the spaces between the points could be really far apart dimensionally.
Yeah.
Yes.
And so the more that you have, the more difficult it is to see it. You know, with 10 you can have an idea. I think 10 is too many here even. Because again, what's happening here is that you have to make like a summatory for all the attributes. So when you have 10, you have to kind of say, okay, if these points are on the top there, close to this, to the number, I don't know, time 1 hour, I guess that dimension has to be higher. Because you can see that there is like this angle with the next one that's kind of big, and that tells you that. But the moment that you go to that one there, that you have 2, 3 so close to each other, you cannot detect which one is the most important, because you don't have space. So yeah, you have the same problem here. When you have a lot of dimensions, it's very difficult to know what it's telling you to do. And also the position of those dimensions changes a lot. I don't know if they mentioned that in the video, but it's not the same thing when the order changes a lot the position. So if you have like 2 attributes on the top and you change one from one in the bottom, that could change totally the position. So they are not playing with that. They are making some calculations here. I mean, this is a specific application. I didn't went into their paper. But here, this is what I wanted to show you. So the way that you kind of play with it, because again, it's very difficult to know what's happening. So what you do is you can have like some interactivity. So you say there, they show a scale. So you can pull attributes farther from the point of the middle or put them closer. The closer, the lower that value, the farther, the higher that value, and then all the points move with that. So you can see there how they are like kind of moving around. You can rotate them, so as you can see the position change a lot the values. You can put one on top of the other, and then they do a union with those 2 attributes in that dimension. I don't understand exactly what they mean by separation. Well, you can remove some of them from the visualization and it changes. So that's kind of what's giving you the idea. No? You have to move the things around, and while you're moving things around, you kind of give an idea of, oh, this dimension is more important than the rest because it's moving everything with it. So it has to be like the most important one, or things like that. But again, if you see the interactivity that they have here, they don't plot 200 dimensions when they are doing this. They plot 5 or 6, because if not, it would be almost impossible to see what's happening. And again, when I've been working with these things, it changes a lot the position. So if you kind of put this value here and change it to the other side, you might get something entirely different, because it depends a lot on how these attributes are correlated between each other too. So then they do like this user study with NBA players. I don't know if there's something, okay, they show it a little bit more here, but I mean, it's the same idea. So you can see there that they have the points, they hover on top of the attributes to see what that dimension is doing to them, and then you can move them around and position them, and then the points get positioned. And that's giving you kind of some information of what's happening in the visualization, but it's not clear. You know, you can have an idea of maybe this attribute is more important, but you have to spend time looking at it. That's why they kind of call this visual analytics, because you should be like looking at this and then looking at the numbers, going back and saying, oh, this doesn't make sense and stuff like that. It's kind of more exploratory than for telling somebody what you discovered.
So it's more art than science?
I think this is more science than art. In visualization, they have like the 2 things, in the sense of when I do things like this, that is kind of visual analytics, is kind of more scientific, because you're looking at trying to find something. When you want to transmit some information to somebody else, it's like more artistic, because you already know what you want to do. And it's kind of, how do I paint this pretty to make this line really high, so that you say, oh, we are selling more stuff, you know, and putting a line really high up. So that's kind of the other part of this. So they call that like informative visualization, and they call this visual analytics. So they have like 2 parts of it, but it's
What was the first one?
formation visualization, I think they call it information visualization.
Okay.
Yeah, that's kind of the newspaper stuff that they do to show you things, and and to CEOs and things, things like that. So for you, I mean, this is really funny, because in this world you have like things that are powerful but difficult to understand. So people like CEOs won't like that. They want to see a bar chart and that's it, you know, a line chart. And then when you're working with something trying to understand the data, then is when you use like maybe things like this. But in reality, when you prepare dashboards for people and stuff like that, they want line charts, histograms, bar charts, and maybe pie charts. And then you have to tell them no pie chart. It's kind of that fight, yeah. We don't think pie charts are really nice, that's why I say that. So so that was star coordinates. Then biplots, it's kind of the same idea. This guy said, okay, instead of doing exactly like star coordinates, we're going to make a different kind of projection. But we're going to still put those attributes there so you can play with them. So basically the projection that I use here is PCAs. The problem with biplots is this, I mean, it's the problem I have with PCAs is that if you have more than 2 PCA vectors that are important, so your 2D of your drawing, then you lose that because you're going to paint in 2D and then you're going to lose the other dimension. No? That's what they are saying here. And again, the same problem with the scatter plots, that points that are close to each other because you're only looking at 2 dimensions, they might be very separated from each other. This is more from a statistics technique. Here, as you're going to see, it's very, very similar, the idea. They put the, so it looks the same, just then the way that they do the projections is different. I'll make this big. Okay.
It's a bit like a star.
Yeah, so you see it's very similar to the star coordinates. You have the axis here drawn, but then the projection of these points here are not based on that vector summation, are done with PCA. And then, I mean, it's easy to interpret again that this, for example, this arrow here is funny. Sorry that you don't see it very well, but then you have the Simpsons and Family Guy, so they say Family Guy is more funny than the Simpsons, and then both of them are much more funny than House and CSI or American Idol. No? So again, you have a kind of the same idea here. Things that are down here, like American Idol, seems like more kid-friendly or maybe inspiring and less interesting than a House. Or CSI seems like really interesting, but not at all, what's this here? Relaxing, I think it says there. So that's kind of the idea you're getting here. No? So you kind of get the points together. You know, it seems like CSI and House are more similar, Simpsons and the Family Guy are more similar, and Dancing with the Stars and American Idol are more similar. And you get like a little bit of that idea that these dimensions here are more important than this one here. This is controversial, I think this says there. Again, they add interactivity so you can play with the stuff and move the things around. I think basically what they are telling you in the video here is that the way that you understand the graph is you make a projection on that line. So if you want to understand how funny the movie it is, so you would make like funny axis really large, and then you make a vertical projection of all of those values there. And then you get like kind of the relative funniness of that series. So again, it's very similar to the previous one. The only difference is that here you're not making like that simple vector summation. You're making like this clustering thing that optimizes the clustering in a sense. So with the previous one, you wouldn't get like optimized clusters. The points would be similar to each other, but maybe you have a lot of cluttering. All the points are together. With these things, you might get like separated clusters better.
What is the input data for this one? How did they come up with this?
So it's the same thing. You begin with all the multidimensional dimensions that you have, but then you will run PCA. So instead of projecting on each of the dimensions, you calculate the 2 PCAs. You put the points in the PCA, and then based on your origin, you position all your axes. I don't have a clear idea about this. Now you ask me, I'm going to tell you. I don't have a clear idea of the order of the axes, of how they decide. You know, on the previous one, you could put the axis on any order. And once you have the axis drawn there, you would do your vector summation, and that would position your points. Here, I didn't get an idea of how they are positioned in this axis. I understand how you put the points, because that's the plane. You have the PCA, then you have your points. But then I don't understand how they decide that this one goes there, this one goes there. I think that's part of the algorithm. I'll probably do another process with the axis to do that and position them. Because after these guys came up with biplots, these other guys, if this wants to go to the next one, okay, created RADBIS. And RADBIS is a very similar approach from biplots. These are more special things that has 2 or 3 things. They are not so much, you don't see them so often, but they're kind of what they show up in the visualization conferences. Here again, they do the same thing. Instead, the axes are not drawn anymore. You do PCA with the points, so you position them in space. Then your axes or your attributes are going to be positioned in these 3 concentric circles. So you have different dimensions here. What they are showing here, it's like each of the circles is 1 dimension with different classifications. You're going to see when I play on it. So I think one of them is like the first thing they begin doing is with trigonometric forms. So you can see that they are selecting different attributes, putting them there. What it says here on the top is pentagon. Let me tell you what's saying there. This says pentagon. Can I put this in a little bit higher quality? No, that's the maximum quality. Okay. So that says triangle, that says polygon, that says circle, and I don't know what that says there. But basically they are putting all these attributes, I'm guessing the data points, each of them are different figures, and then they get positioned depending on how close they are to being a circle or a triangle. So now it seems better. Once they define the different axes, these 3 axes that you're seeing there is if you've ever done virtual reality or done things with 3D, and you have like 3 different axes that you're rotating around to rotate the 3D, that's kind of what these axes are representing. So it's a bit weird because you're seeing everything flat. Once now you'll see that they begin moving these points around, you can drag them around, you'll see how this begins like kind of rotating. So that's how they kind of play with the visualization. It's going to happen in a second. Okay, I think it's going to do it now. Come on. Yeah, so you see there it's touching the position, and you see how they are rotating. The visualization rotates with it. My impression here is that it's difficult again to visualize because you don't have the axis. But you can move things around, so you can create your own clusters. That's kind of the idea here. That thing that they are doing there is a non-linear transformation that they have, and that's why this is nice. So RAD-based usually is used when you have like very sparse clusters or separated clusters that you cannot detect with other things. If not, usually you don't use this one, and you would go with the previous method that I described. They do the same thing now with another data set of people in Dortmund. So again, you see the 3 concentrical values, and then different types of clubs here, or music in the clubs, people that go to that club, and then the type of people. This is party, aggressive, relaxed. And they playing with those values, they begin creating different clusters by rotating them around. So you see there how that's kind of tilting this way. So again, it feels difficult because for me, I've seen this axis a lot of times, the circular axis to rotate things in 3D, and I don't have a clear idea of what they are doing.
Yeah, I don't get a good sense of the...
You can only see like how things are moving when they are rotating a little bit the thing, and you have to like rotate the visualization a little bit and then play with that too, but you don't know exactly where the axes are oriented, so you're trying to separate clusters by hand, kind of. So this would be maybe you know the clusters, or you know that there are some clusters there, and you're playing with the numbers trying to separate them. I think, again, this one, I've never used this, and don't feel it's really nice, or I don't understand really the concept compared with this one. I prefer to have the axis there, and this gives me a better impression of what this one does. And then I think this is almost the last one. This is something that I found this year. It's actually from last year, but it's pretty nice. So these guys call this the data context map. So I've been saying all the time now that these projections, the problem that they have is that you lose the information about the attributes. So these guys were like, okay, we lose the information about the attributes, how we can prove that? So they said, okay, we're gonna do a projection based on the data similarity, and then we're gonna do another projection based on the attribute similarity. So they do that for the data points, and then they do that for the attributes. It's going to happen in a sec. So, well, the idea here is they are trying to select a university. So they are saying, okay, when you have to select a university, you have a lot of different parameters. It's difficult to choose what you want because some of them are going to be against the other parameters. So it's difficult to choose where. When you have the projection that is going to show in a sec. Okay, this is all the database. Now it's going to be like, oh my God, it's very difficult. So you can see here, that's kind of you begin with the stuff and you get an initial projection like this one. No? So as we were been saying all day, we know that USP, Berkeley, and Harvard are similar to each other, no? Because they are close to each other. So they are more similar at least than, hey, don't go, than sorry. So they are more similar between each other than Texas or Virginia Tech that are down here. That's obvious. But before you didn't have any of these attributes here. So you didn't have any information about what relationship the attributes have between each other. If we look now only at the attributes, they look at the similarity. So with that, this means that up here, tuition, score, PhD, faculty, and academic are related somehow to each other. So let's explain how they are doing this. When you're doing this with data, usually in similarity, what you look is at each of the data, and you see all the dimensions of that value. So data 1, data 2, data 3, and then you compare all of them together to see how similar they are between each other. There is another option. That is, instead of looking data by data, you look attribute by attribute. So you look attribute 1, all the data, attribute 2, all the data, and then you compare those columns between each other. So that's what they are doing here. They are comparing the tuition column with the score column. And that seems that high tuition is high score, low tuition is low score, high PhD is high tuition, high score, and so forth with all of these ones here. And the same thing with all of these things here. So I mean, it makes kind of sense, no? In nightlife and athletic, it seems that they are higher. So when you have like good athletics, usually there is good nightlife. When you have, I mean, all of these ones kind of make sense. So you have higher scores, tuition is usually more expensive. Usually you have better PhDs and faculties in those universities, and usually there are more academics trying to go to that university. So here on the right, what you are seeing is like all the database, no? So we've seen that we projected this in 2D. We have to imagine that our visualization size is this one until the top. So that's kind of all the dimensions now are in this space here. And we know that some things around here, you know, have to be related with nightlife and athletic because they are close to here, these values, but you don't know how. So the way that they come up with this is they created kind of color mapping now. So these are the filters. So for example, for income, this is like 0 income, maximum income. So you can move these sliders up and down. When you begin moving these sliders up and down, you're going to see that when it's at the beginning with all the information, a blob appears, selecting like everything. That's going to happen in a second. I think they do that with tuition because I think that's the one that he's interested on. So he's talking a little bit about what I was saying before. Let's go there. Okay, so he's saying, see, I'm interested on looking at tuition. So you see there the filter. The moment that they touch the filter, there it is. You have all, so this is telling me, okay, all of that tuition, covering all the tuition that I have here is all of this. They know that because they know the individual values of these values here. So when they begin reducing that value there, you see how it's getting smaller? Yeah. So what he's doing is making that filter smaller. You're getting this graph here. And then this is telling you the context that you didn't have before. So this is telling you that, I don't know where it is now, but at this value of tuition, all of these values here are covering all of these ones. So these ones are the highest ones. You got rid of all of those. So he continues because he wants a lower tuition. So he continues to make it lower, a little bit lower, a little bit lower, and you can see how it's changing. The only way that the way that they are doing this is just they're looking at individual data points, and when they go lower that point, they basically grab that part out of the space. So they are faking because you don't know that, but this way you get like a good idea. Because now, imagine that you're in this spot here. You want to choose some university. Before, you knew that these universities were similar, but you didn't know how similar. Now when you're filtering that up and down, I don't know exactly which ones disappear right now, but imagine this one was green before and now it's not. So you know that things that were here are even more expensive than things that are here because you're making it tuition a little bit smaller. So you can have an idea of where to look, and that's really important because you're trying to search for something that tells you something. So you know that these things are similar to each other, and you also kind of know where the space is moving around. So this is nice with one, but it becomes really interesting when you do more than one. So imagine that that's your maximum tuition that you would pay for your university, no? So you know, okay, I'm going to select a university that's around all of these points here, because those are the ones that have the tuition that I want. But then maybe you also want to see, I think it's going to do it in a sec, it's kind of seeing the values now and saying, see, all of those values are smaller than the tuition that I selected. But I'm also interested in high academics, no? So now I'm going to do the same thing with academics. Now I have all the values of academics and I'm making them higher on the top here. So I'm selecting lower values and I'm filtering them out. So now you see that this other color got embedded on top of the other one. So now the good thing is that this map begins to get smaller. So we're looking at academics, so it makes sense. You're making it from the smallest ones to the bigger. So you see this point here that is very far away from academics. It's obviously out right now because it's kind of the lowest values of academics. The lower that this would get, the smaller the blob. But it's giving you that information of what points you can select, and maybe that's your good academic score. So look, now you know that this point are useful to you.
Those are the intersections.
And you didn't know this before. So it's a very simple approach to doing this. They didn't do anything special. They didn't do anything special algorithm. They just came up with a good idea of how to put both things together. So then the third option I think they look for is what is in athletics, I think. Yeah, so now he's also interested in athletics. So now you filter also in athletics the lower values of athletics until the point that you want. And then you see again the blob, the pink one gets a little bit smaller, keeps getting smaller until he finds the score that he's looking for. And then basically you can see here that the university that's here is the University of Virginia, is the university that has the 3 blobs one on top of each other. So it has the blue, has the green, and it has the red one. I mean, this is a specific example, but the good thing here is that it gives you this thing that you can understand what's happening just moving the spaces bigger and smaller. And that's something really nice because, again, with the multidimensional data, that's something that you lose. And again, it's just a clever idea. It's not like a different algorithm, or they did the same thing as the others, but then they projected also the attributes, and then they color code the stuff based on what data points you have in that region. Okay.
That's very nice.
Yeah, I like this one a lot. Yeah, I like this one a lot. It was really, really nice. I mean, they did 2 or 3 approaches to this before, similar maybe to Radbase. They were rotating stuff too, but it looked very weird because they tried to do it in 3D in the 2D display, and then it's very difficult. Yeah, and this thing, I mean, thought it was very interesting because of that. I've never seen like embedding both things together, and so that's why it's called data context map. And I mean, that's the last one. I put also a video here, but I don't think we should watch it maybe now. This is kind of more the typical stuff that you see in visualization. So the colors, the light, the brightening of stuff, what you see, because there is a lot of like different details here that the visualization scientific guys talk about. So they're gonna be like, oh, for this thing use color, for this thing use sizes, or don't use pie charts because they are shit. Things like that, I don't know. They are like typical stuff that the visualization guy says. But I thought it would be a bit boring just to talk about colors and so forth here.
Well,
Yeah,
very
that's
good. This is very good. Any questions?
What was the name of that last visualization you showed us?
This one?
Context map.
Yeah, that's awesome.
Yeah.
It's so simple too.
I know.
Yeah, it's a very, very good idea. So, I mean, I made this presentation because I'm writing a paper about this. I sent it to him, and that's why I'm here now. And I was writing the paper, and I went to the visualization conference last September, I think it was. And I go to this tutorial about multidimensional data, and it's about the guy that wrote this paper called Klaus Müller. And I'm looking at all the stuff, and when he comes to this thing, it was like, ooh, that looks like so similar to the things that I'm doing. I never heard this before, and yeah, I got really happy with it because it seems really simple, because in reality you don't know that. So the space here that they are drawing, all of those things is fake. They don't know it. They just say, okay, if you know that these data points have this threshold or these values, you know that data points around here have to have high values.
Cool. Is this something that's publicly available?
The codes, I don't think so. This kind of guys, you might find some of the ones that I made here like a tool.
I mean, the older ones, definitely. Most of them, they're packages to do it.
What I don't know, so this one specifically, I don't know if they released a package, to use.
16.
Yeah.
Probably check on the author's website.
Yeah. But
see whether they release anything, or they might have an online.
My impression is that they're gonna have the same data. I don't know if they are gonna allow you to import new one. I mean, it would be cool actually because I didn't think about that, but it would be useful for me to use it actually.
Yeah, good way to find a good school.
Yeah.
I know.
Yeah.
Well, they said the TSNE was at least part of TensorFlow.
Yeah, TSNE is open. You can find it, for example, in Python too. You have them. There is something in Python called like manifolds.
Yeah,
blah blah.
There is multiple
You have it.
packages. I put a link on the course website. If you go to, I think I put it under dimensional reduction. You go there. I have a link to the TSNE, one of the authors' website. He has a website for TSNE, and he lists all the packages.
I mean, it's probably just running a function, but it's gonna be depends on your data. But they say that it's long, so I've never tried it yet. I want to, but
Yeah, and obviously, as you saw, right, you have to run it multiple times because each time you might get a different
result, yes,
Different
and you have
result,
to play with those
yes.
values, yes.
Yeah.
So that's why I liked a little bit this guys here, because with these guys here you can get a better approach from that. Because if you imagine that you do the same thing, and then you don't have the manifold, remember that they have that number there that you have to play with to see the clusters. That would change also the values of that lobs. So if you would do the same thing with that one, you could see the same thing on it.
Yeah.
So I don't know. From what I worked with this, I thought this was very good because when you're looking for something, usually you don't know what you're looking for, and usually when they explain you this, they assume that you know what you're looking for. You're like, you have two clusters, you're gonna separate them and you finished, but that's not what you're looking for. You're kind of, this kind of was kind of an assumption stuff, but usually when you're looking at this, you don't know what you're looking at. So it's, at least playing with that, it gives you like an intuition of where the values are. Yeah. And then if you have much more dimensions than this, it helps a lot because you can get like that idea.
Cool. Thanks. Other questions? Okay, well, thank you.
Are you gonna have these slides?
I'll send it to you.
We'll link it to the website. Okay, so yeah, that was a great introduction because lots of stuff that I don't know about, so that's fantastic.
Yeah, how come you don't do that kind of stuff, man?
I'm not cool like Jason.
And people are like, well, what's your research? It's nice, what's your research?
Okay, so like I said, actually on the course website, there's a lot of info that I kind of put there. I collect all my links there as well. So like just before this, we're talking about image processing. I've got a page where OpenCV, SimpleCV, some of these techniques, and SIFT. So again, if you need ideas for what features to pull from image data, look up some of these things. Some of it is very specialized, but yeah. I know last time somebody asked about audio data, right? And I do have a page there as well. There are different features. Again, like I said, the one that's most used is MFCC. That's the most used right now. It's kind of like almost like the de facto audio features that's used for voice recognition and whatnot. But if you are looking into specific stuff, like you want to do some music stuff, like give an MP3 file, try to figure out the genre or the beat and whatnot. There are other types of packages. There's a music analysis, retrieval, and synthesis for audio signals. Go take a look at this. Again, just very quickly, since we do have a little bit of time, just a few minutes, right? For example, what does a music file look like? You could, okay, so for example, this is a sound editor. It actually shows you what the music data looks like. So I'll just kind of show it quickly. I downloaded an MP3 so that you can look at it. I think it's open recently, yeah, here. For example, right? So this is the song from the Disney movie Trolls. This is what it looks like. That's what sound data looks like. This is stereo, means there's actually two tracks, right? And sound, if you remember from physics, is just displacement or vibration, right? So it's just this axis is time, and then it depends how often your signal is sampled. So this is a this is the sort of the something of the sampling rate, and then each amplitude is a 32-bit float, pretty much. So this is what sound data looks like, right? You can play it, and
do you really think I can be happy? Of course, it's inside you.
That's what it looks like. So when you play this is what it sounds like, right? But other than that, this is just a huge array of floats. So how are you going to pull all the different things that you hear? So that actually relates to sort of psychoacoustics as well. People looked at, how do you map the things we hear to this? And in the case for sound, for example, there's the Fourier transform that will actually extract the frequency information, right, and stuff like that. But if you want to look at beats and all that, that's even more involved. So you can zoom in and see at the sub-second level what does the waveform look like and stuff like that.
Why is there two copies of it?
Because it's left and right channel. It's a stereo track, right? So it's left and right. Yeah.
It's not mono.
Yeah, it's not. Good one. All right. So yeah. So look at some of this. There's packages again. There's music tools in Python, packages for you to extract features from here. So there's a lot of tools. The good thing now is that, I mean, 10 years ago you have to write all this yourself. Now it's like a lot of these tools, libraries are available. So it's just amazing. All right. And just quickly again. I think I put some of these links in dimensionality reduction. This is the website on TSNE. I think this is the video that was showed earlier. And there's a survey paper as well. So this is the TSNE website. Has the papers, has the implementation. So there's a bunch of implementations from MATLAB, CUDA, Python, and so on. Okay, so all the resources are there. Okay. Otherwise, that's it. So next week we're going to do project presentations, about 12 minutes each. All right. I will send out an email confirming all the folks who are presenting on which days, later today or tomorrow. And if you have any request issues, let me know. Right. Otherwise, we're going to project presentation mode. Last week of instruction. All right.
Anybody on Monday want to switch to Wednesday now?